Good day, students. Welcome to our second session for the course Digital Logic Design, offered by the Department of Electrical and Computer Engineering. This session is in continuation with our previous session covering combinational logic design. So, in this session, we will be discussing some variety of circuits that are related to the combinational logic. Let us look at the contents which we will be discussing in today's session. So, first of all, we will be reviewing our previous class, what we have learned in our previous session. Then we will discuss the concept of carry propagation, and we will discuss and design a carry look-ahead adder that is utilizing the carry propagation concept. Then we'll switch to the binary subtractor, that is a circuit that has the capability to perform the subtraction operation, and we will be discussing that circuit that has the capability to perform addition as well as the subtraction operation at the same time. At the end of our discussion, we'll switch to the decimal addition, and we're going to add two decimal numbers, basically two decimal digits that are being encoded in the binary coded decimal, and we will see if when the result is exceeded from the value of 9, how the decimal value is adjusted in order to generate the correct BCD code for the output. So to start with our discussion, we will first see the reference settings and acknowledgements. Basically, we will be discussing chapter number 4 from the book Digital Design with Introduction to the Verilog HTL, and the content of the slides are being taken from the book as well as the slides which are originally generated by Morris Mono itself. So let us first review what we have learned in our previous session. We have learned about basically the design principles that are being used in order to design the combinational logic circuit. Then we've discussed a variety of examples in which we've practiced those design principles and used those design principles in order to design the combinational logic modules. And we have discussed variety of circuits that are used to add the binary numbers or the binary bits. The circuit that has the capability to add two binary bits is known to be the half adder circuit, and then we move further with the 3-bit binary addition, that is a full adder circuit, and then we've discussed the binary adder circuits that has been shown on the current slide that has the capability to add multiple binary bits. We have discussed a 4-bit adder circuit that has the capability to discuss two numbers of 4 bits each, and today we will be discussing the concept of carry propagation from the same content which we've discussed in the previous lecture. You see the setup that is being shown in the current slide that is being used for the binary adder, that is utilizing the 4 full adder circuits. The carry is being propagated from one full adder to other full adder, and in ideal cases the delay in order to generate any output is zero, but in practical cases each digital module do utilize some processing time in order to produce the outputs. So we will see the impact of this delay. If this delay value is more, do the output produced are reliable or not, because the digital system, there are many constraints that are involved while designing the digital system. Sometimes we are focusing on the speed, sometimes we are focusing on the reliability, sometimes the cost element is important, and in this circuit basically which we've discussed here is basically in which the carry from the first full adder is being propagated to the next full adder and the next full adder, and so on and so forth. If we assume that the full adder circuits are taking the minimal time of, let us assume for the example of 1 microsecond each. So the first full adder will gonna generate the correct output after 1 microsecond. The next full adder definitely will gonna produce the correct output after utilizing additional 1 microsecond, and so on and so forth. After 4 microseconds that are being processed, the correct output is generated. What will be the status of output before the 4 microsecond? That is important to observe that, because before 4 microsecond the carry outputs are not being generated properly, so the output that is being calculated before 4 microsecond is not the reliable output. So that is a point of concern. How to avoid this scenario so that the circuit propagation delays and all the constraints are being avoided? That is the important thing which we have to discuss in today's discussion and class. Here we will be using the carry propagation concept, because in order to add two binary numbers in parallel, that implies that all the bits of the augment and addend are available for computation at the same time. So in this case, if we look at this scenario, this particular scenario, uh, this carry is being propagated from this full adder, coming from the input from this full adder, so on, from the second full adder, from the third full adder, and the fourth full adder, till the final carry. So this is basically the longest delaying path in a circuit, and we have to meet this constraint in order to produce the correct output at the same time instant. So in any combinational circuit, the signal must propagate through the gates before the correct output sum is available in the output terminal. That is important. How we're gonna address this issue? Uh, Basically, the critical path in any digital circuit, that is basically the worst case scenario, is the longest propagational path or the longest delay path that is basically constraining the speed and the efficiency of the of our circuit. And we have variety of ways to reduce the critical path. We can introduce the sequential components in our circuit in order to reduce the critical path. We can use the concept of pipelining in order to reduce the critical path, but we will be discussing these concepts later in our later sessions. So in the previous session, if we see the critical path or the longest combinational path that is a, in that exists in the previous circuit, that is from A1, B1, C1, then uh, the carry is being propagated to C2, then C3, C4, and then the final carry. That is the longest delaying path. So this is the constraint which we have to meet in order to produce the reliable output. So this is basically constraining our speed of our system, and the efficiency of the system is affected in that scenario. In those circuits which has the longest combinational delays, the speed definitely is less as compared to the circuit that has the lesser combinational delays. So we will basically look ahead in order to generate our carry, and we will propagate our carry. We will use the concept of the binary bits addition at the same time instant, and we will see if both the binary bits are 1, then there is a chance that the carry is being generated in the circuit. So we will produce that carry, and we will forward that carry to the next successive addition, so that the addition can be done without waiting the result of the previous adder carry output. So the carry propagation delay can be avoided to employ some faster gates. We can avoid this propagation delay by using some faster gates, or we can use a look ahead carry mechanism. That is basically the mechanism which we will be discussing in today's discussion. So the point is that carry look ahead mechanism is faster mechanism, but utilizes more number of resources, which we can see while implementing that setup. So we will be using the concept of two Boolean expression, that is when the carry is being propagated and when the carry is being generated. So we use two terms, that is pi for the propagation of the carry, and gi, that is for the generation of the carry. So there is a case when both the inputs ai and bi at any time instant are 1, then carry is being generated and being applied to the addition operation instead of waiting for the propagation. So the sum expression for the full adder setup is equivalent to pi exclusive or ci, where pi is a propagation carry, that is basically the exclusive or operation between two input bits at any time instant, that ai exclusive or bi at the same placement. And the next carry is expressed as ci plus 1, that is equal to gi or pi and ci. So these are the same terms which we've discussed while discussing the expression of the full adder circuit. So there is not much difference while discussing these two terms. So let us see what are the terms that are being used in order to produce or run in order to generate the carries. So C1 can be expressed as G naught or P naught and C naught. C2 can be expressed as by these expression can be expressed as G1 or P1 and C1, and if you place the value of C1, this value C1 in this expression, then we got the final term that is being used to produce C2, that is G1 or P1 and G naught, or with P1 and P naught and C naught, and similarly C3 is being produced here. So these are the terms, these are the expressions that are used to produce the carry outputs. So this is the setup for the carry propagation in a carry look ahead adder. P1, P0, P2, and G1, G0, G2, and C0. These are basically the terms that are being discussed previously. Uh, if we see the terms, the generate terms and the propagate terms that are being implemented in those expressions as well, which we've discussed earlier, and this is the setup that has been used to produce C1, C2, and C3. So let us see the detailed setup that has been used for the carry look ahead adder. So that next diagram, that is basically the detailed diagram that represents our 4-bit carry look ahead adder. If we see the terms that the inputs are being applied to this setup, and if you see that this setup resembles to our half adder addition, if you remember the basic addition of the two binary bits. So these terms basically contributes are the generate terms and propagate terms that are being applied to this carry look ahead generator, and this carry look ahead generator basically covers the previous circuit which we've discussed right now, and the correct carry and the sum results are being produced. So if we observe this circuit as compare while comparing to our basic binary adder circuit, so it's much more complicated as compared to the previous one, and more number of resources are being utilized. If you see the number of resources or the number of gates that are being utilized in this setup are much more as compared to the previous setup. So we are compromising on the cost element, but at the same time this circuit is much more faster and much more reliable in terms of speed and efficiency as compared to the previous one. Now let us see a circuit that has the capability to subtract the two numbers, and if we see the concept of the subtractors, if we have the ability to subtract two binary bits, that circuit is known to be the half subtractor circuit. And if we have the capability to subtract three binary bits at the same time, that circuit is known to be the full subtractor circuit. And same concept is being applied while designing the full subtractor circuit or the half subtractor circuit. The same concept which we have discussed while designing the half adder circuit and full adder circuit. So let's go into the detail of the binary subtractor circuit uh, that has the capability to subtract two numbers. And we've discussed earlier that how computer systems are going to perform subtraction operation, since the subtraction is the case of addition. If we are performing the subtraction of two numbers, basically what we are doing is that the number possessing the negative sign, we are representing it into its two's complement notation. So what we have to do is that we have to generate the two's complement of that number, and then we're going to add with the first number, and that addition result is basically our subtraction result. So if we see the setup that has been used to perform the subtraction operation, what we have made changes in the previous circuit which we have discussed in order to add binary numbers is that we've used some bunch of exclusive OR gates, and which are used to generate basically the ones complement of the number in case we have to perform subtraction operation. And for the subtraction operation we have to perform two's complement, that is the in which we have to add one in the ones complement in order to generate a two's complement. If we see the setup, that this M is a control line with a control signal that is responsible for the circuit to either operate for the addition operation or for the subtraction operation. If the value of M is equal to 0, then this circuit will behave as the basic adder circuit. The both inputs A and B are added, but one this input is being switched to logic high or 1, the same circuit behaves as a subtractor circuit. So how this circuit will basically work, first of all let us see the behavior of these exclusive OR gates which are connecting these B inputs at the time instant and the M inputs and producing the output for the full adder's input. So if we see the behavior of the exclusive OR gate, let us assume this is the exclusive OR gate. with two inputs, and if the value of m is been set to 0, whatsoever we will apply the input, if the input is 0, the output is 0, and if the input is 1, then the output is 1. It's just behaving like you can say a buffer. It is just forwarding the applied inputs to the outputs without complementing the inputs. So whenever the m is set to 0, this b0, b1, b2 and b3 is forwarded without complementing process. And if we set this value to if we set this value to 1, then if the input is 1, the output of this exclusive OR is equivalent to 0, and if we apply the input 0, then this output will be 1. That is basically acting as a NOT operation or the inversion operation or the complement operation. So whatsoever the input is applied on those exclusive OR gates are being inverted when the value of m is being set to 1. So let us see how this circuit will work. So if we set this value to 1, this input goes to 1, this input goes to 1, because these all inputs are connected with each other. This input goes to 1 and this input goes to 1. So the output of this exclusive OR gate is basically, this is B naught prime. Similarly, this will be B1 prime, this will be B2 prime, and this will be B3 prime. B naught prime will be added to A naught, and 1 is being added, that is being applied to the carry. That is basically in order to generate the second complement or the 2's complement of the number. So the 2's complement is being generated and added with A naught, A1, A2 and A3, and now this S naught, S1, S2 and S3 in this scenario basically represents our difference operation or the subtraction operation or the subtraction result. This gate is basically used to represent our overflow operation. If we add the two numbers of the same size, the result can be a 1 bit extra as compared to the size of the input. So this B bit basically represents the overflow operation in order to represent those scenarios in which the overflow can exist. So student, let us move towards that another example, that is a circuit that has the capability to add the decimal numbers or the two binary coded decimals. Decimal ladder basically is an adder circuit that has the capability to add two BCD numbers, and we discussed that in our previous discussion that whenever the result of the BCD number is greater than 9, we need a setup that is used to adjust our BCD number. So this circuit has the capability to add two BCD numbers as well as to adjust the result. So if you see the number of required inputs and outputs, uh, since each decimal digit is encoded into 4 binary bits, and each BCD code is of the 4 binary bits, we've got 9 inputs, 2 BCDs and 1 carry in. So 2 BCDs of 4 bit each and 1 carry in, and we've got 5 outputs, 1 BCD and 1 carry out, in order if the result exceeds the summation of the value of 9. So what are the design approaches? How many number of entries that are being used for the full binary full adder? That is basically 2 raised to power 9 entries that can be generated in the truth table, that are quite a lot entries. And we can see that if you are adding the two decimal digit at a single placement, the result can be equal to 19, because 9 is the maximum value in any single placement. So 9 is being added with 9, and if there is an addition carry that is being propagated from the previous addition, then the maximum result that can be produced at the output of this decimal adder is 90. So let us see the truth table and the terms that are being used while discussing the circuit. We will be discussing the circuit later on. So Z1, Z2, Z4 and Z8 are the terms that are basically representing the binary sum if you are adding the two BCD numbers, and K if they produces some carry. 1, 2, 4, 8, basically these are the placements or the weight that represents the weight of that specific binary bit. And if we are adding a result two BCD numbers, the result can exceed the value of 9. So in those scenarios when the result exceeds 9, we have to adjust our result in order to produce the correct BCD number. So for all those cases, for all those binary values that exceeds from 9, for example 1010, that is the binary value of 10, and similarly that binary value of 10011, that is the binary value of 19. So in all those scenarios we have to adjust our result, and by how we're going to adjust our result, we have to add binary value of 6 in our result in order to adjust the BCD number. So if you see the scenarios, if you see the setup, what are the cases that are being observed or being followed while designing that setup? If we observe the first thing, that the carry is being produced for the variety of the cases. For example, these last 4 cases, the carry is 1. Similarly, Z8 and Z4 are 1 for these particular scenarios, and Z8 and Z2 are high for this particular scenario. In all those scenarios, we have to add the binary value of 6 in our result. So what are the modifications that have been needed, which I've discussed? Whenever the value of C is equals to 1, or the K equals to 1, or the product of Z8 and Z4, that is the AND operation, that is equal to 1, and Z8 and Z2, that is equivalent to 1, we have to adjust our result, and we have to add the binary value of 6 in our result in order to adjust our BCD value. So this is the setup. So let us try run this setup, this system, in order to see how the setup will work. We are utilizing two 4-bit binary adders. The first binary adder is used to add these two numbers, and the second binary adder is used to adjust our result. So this is for the adjustment of our result, and this is for the basic addition result. And let us see with examples, if we are adding the two numbers, how the circuit will behave and react. So coming with the example, let us assume that the first number is 1 0 0 1, and the second number is 0 1 1 and 1. If we add these two numbers bit by bit, starting from the least significant side, 1 is being added with 1, so 1 plus 1 equals 0 with 1 carry. So 1 plus 0 plus 1 equals 0 with 1 carry. 1 plus 0 plus 1 equals 0 with 1 carry, and 1 plus 1 plus 0 equals 0 with 1 carry. We can clearly see that this result is greater than 9. So in that case, if the result is greater than 9, we have to adjust this result. Now if you see at the circuit, these bits are basically, this is Z1, this is Z2, this is Z4, this is Z8, and this is K. So since the result is greater than 9, we have to add the binary value of 6 in the result, that is 0 1 1 0. Now the result is 0 plus 0 equals 0, 0 plus 1 equals 1, 0 plus 1 equals 1 0 plus 0 equals 0, and that was the final carry that was being produced in the previous edition. So if we see the result, this is the BCD code for 6, and if we append the 3 zeros at the most significant side of this one in order to produce a 4-bit BCD code, so this is the BCD code for 1. Now the result is 60. That is the adjusted result. So if you see, if you try run these inputs in this circuit, this input is 1001, next input is 0111, and the carry in the default carry in the first edition, that is 0. So the value of Z1 is equivalent to 0, Z2 is equal to 0, Z4 equals to 0, and Z8 equals to 0, while K equals to 1. So if we see the AND operation of Z8 and Z4, that contributes to 0, and Z8 and Z2, that also contributes to 0, and this OR operation between 1, 0, 0 contributes to 1. If we see that this output is linked to the input of the second 4-bit binary adder, so 1 is being applied here, and rest of the two inputs of that input are permanently connected to the ground potential or to the logic 0. So this is the code for 0, 1, 1, 0. Now the value of 6 is being added with 0 0 0 0, and the result is being produced as S1 equals to 0, S2 equals to 1, S4 equals to 1, and S8 equals to 0, while our output carry is equal to 1. That is the BCD code for 60. So let us try run another example in which we have these product terms or the AND terms that are being generated in the circuit. So let us assume that the first number is 0 1 1 0, and second number is 0 1 1 1. So if we add these two numbers, 1 plus 0 equals 1, 1 plus 1 equals 0 with 1 carry, 1 plus 1 equals 1 with 1 carry, and 1 plus 0 equals 1. This result clearly is greater than 9 with no final carry is being produced. So since this is greater than 9, we have to add the binary value of 6 in it, 0, 1, 1, and 0. So 1 plus 0 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 0 with 1 carry, 1 plus 1 plus 0 equals with 0 with 1 carry. So the final result is, this is the binary value of 3 and 1. 13 is the adjusted result. So if you apply these input on this circuit, that is 0 1 1 0, along with 0 1 1 1, Z1, Z2, Z4, and Z8 are equal to 1 0 1 1, and this AND gate now produces 1, this is 0, and this is 0. So this 1 is connected with the input of the second 4-bit binary adder. So the 6 binary value of 6 is added with the result, and now our final result is 1 1 0 0 with our final carry. So this setup is used to add two BCD numbers, and result is adjusted in all those scenarios in which the result of addition exceeds the binary value of 9. So if we have to add multiple decimal digits at multiple placement carrying multiple weight, then this setup is replicated for each specific placement. So that was all for today's class, for today's session. I hope so. The addition operation is much more clear to all of you. Let us conclude our discussion what we have learned in today's class, and then we'll see what are the reference readings which I recommend you to read uh, before coming to our online session discussion sessions. We have started our discussion with the basic adder circuit, and we've seen the concept of the critical path, that is basically the longest delaying path in a circuit. And as a designer point of view, it is required to reduce the critical path, and we've seen those approaches. The first approach we will gonna see was that to use the concept of carry look ahead adder, and the major difference between both the adder circuits, since both adder circuits have the capability to add the two binary numbers, is that as far as the speed element is concerned, the carry look ahead adder is much more efficient as compared to the ripple carry or the previous adder. But the drawback is that it utilizes more number of resources, so it has the higher cost element as compared to the ripple carry adder or the basic binary adder. Then we've switched to we have moved our discussion to a circuit that has the capability to subtract two numbers, and we've seen a setup that subtraction is a case of addition, and we have not implemented a separate subtractor, but we have performed the subtraction operation by the use of the basic adder circuits. And the point was that we have to represent the number, the negative number, in its 2's complement notation, and then add the result to see if there exists some overflow or not, or the circuit has the capability to add as well as to subtract those two binary numbers depending upon the set controlled binary value that was discussed as the M, that was the line that is responsible uh, to manage the whole circuit as a adder circuit or as a subtractor circuit. And then we've discussed uh, uh, we've switched to our basic our last topic, that was the decimal adder circuit that has the capability to add two decimal numbers to the two BCD numbers. And if we've seen that if the result is uh, greater than 9, then we've seen a setup that has the capability to adjust the number by adding the binary value of 6 in it. So that was all for today's class. As far as the reference reading is concerned, uh, please follow chapter number 4. uh, the page numbers are basically page 157 till page 168. I'm going to repeat that. Please go through the book from page 157 till page 168. Till now, Allah Hafiz.